Wait, what happened?
All right, so new unit. I think you guys will like this. It's it makes a lot of sense in a like intuitive way. So it's a lot of weird shapes like this. Then we're going to connect the shape to like the idea of derivatives and stuff. So let's get into it here. I guess I'll just try to reproduce the graph on the board. So the first question you're probably wondering, if you read the question down there, is what is a F prime number line? What does that mean? Okay, that's my attempt. That's not supposed to be a weird customer. Okay, so you're gonna have to work off this grid here, but that's the number 2, that's the number 1, that's the number -1. I actually managed to do, if I redraw this, maybe it's actually not horrible. Okay.
First of all, is it supposed to be differentiable at 2 or not? Because it looks like right on the edge where because we are quick on me.
Yeah, it's supposed to be. When I made this, I had to make a piecewise function. It's not super easy. But yeah, it's supposed to be smooth. Okay, so what is an F? An F prime number line is just this. It's just a number line that describes when is the derivative positive or negative. So we don't care what numbers, we just care is it positive or negative. Now, of course, okay, well, when does a function change from positive to negative? Or sorry, when does a derivative change from positive to negative? You can see, like, for example, over here, is the function differentiable at -1? Or sorry, -2? No, it's pointy. So on this number line, you're going to put every x value where the derivative is 0 or does not exist. So for this guy, it's going to be -2, -1, +1, and that's it. Did I get them all? Now, Rafe brought up a really good point, which is at 2, sorry, my drawing is not. Let me give it one more try here. I would normally put this in the smartboard thing, but like for the video, it's not really. 1, 2, 3, 4. 1, 2, 4. Go ahead and fill that in if you're feeling confident. 2. This is what I should have done the first time, is drawing the hash marks before I drew all the things. Okay, close enough. Close enough. So is the derivative positive or negative to the left of -2? It is negative. How about between -2 and -1? It's positive, then it goes negative, and then it goes positive. That makes intuitive sense, right?
Yes.
By the way, if you're wondering, well, what is the purpose of doing that? These become very helpful later on when you say you don't have the graph and you're trying to use, say you have a function and you can take its derivative and then test when is the derivative positive or negative. This will help you construct the graph. And even more importantly, this will help you, eventually we're going to move backwards. I'm going to give you a graph of a derivative and you're going to construct the graph of the function, the original function, and having these little number lines will make it really a lot easier. Okay, so F double prime. Okay, now this is where it gets interesting. What do we think? There's a word on here up top that relates to the second derivative. And that word is concavity. Concavity. And concavity refers to kind of like the curviness of it. So let's start off with just this. Anything that's sort of shaped like this, kind of, wouldn't hold water, for example. This would be concave down. Okay. And then if it's kind of like this, like curving up, like a happy, it's concave up. All right, so now what does that have to do with derivatives? Well, do you guys see how on this shape here, the derivatives can be positive or negative? Doesn't really matter. But watch, maybe someone can figure this out. Watch what's happening to the derivatives as I move from left to right across the curve. Pretty big positive derivative. Not so big. Even not so more big. Now it's negative. Now it's even more negative. So what's happening to the derivatives? F prime is
Getting more negative.
yeah, so the word for that is decreasing. Okay, so F prime is decreasing. But wait a second, what does it mean? This is where I try to think high level here. If the derivative is decreasing, that means the second derivative is negative. This is most likely not going to make perfect sense the first time you see it. This is one of those things that you're probably gonna have to, meditate on this one.
Focus the slope.
Well, notice how the slopes went positive, then 0, then negative. But the key is, let me write this in, I'll write some blue here. Would it make sense how, if I said something like f is increasing, so a function was increasing, you'd agree that its derivative is positive, right?
Yeah.
Well, the same thing is true here. If f prime is decreasing, and it's also true, let me clarify this. If f is decreasing, that's a gross letter C there. Then f prime. So let's maybe back up here for a second. How much does this make sense? Like, look back at the first thing we did today. Every time the function was decreasing, the derivative is negative. And every time the function is increasing, the derivative is positive, right? That's a lot like saying, say with velocity, position, velocity, acceleration. If my position is increasing, my velocity is positive. If my position is decreasing, my velocity is negative. Same idea. But then this is just stepping it up one level. This is saying, well, isn't f prime a function in its own right? So if f prime is decreasing, then the second derivative is negative. Likewise, if f prime is increasing, then f double prime is. Okay, so before I move on here, I just want to make sure no one's feeling lost. This is the foundation of everything we're going to do. So if you're lost, let's address it right now. You okay back there? Good. Okay. By the way, do you see the same thing happening? If I look at the derivatives, negative derivative, not so negative derivative, roughly 0. Now it's positive. Now it's increasing. It's still. But do you see how it's been increasing the entire time? F prime. Okay. So, all right. Let's come back to the curve here. So, what do you think is the concavity of this flat line here? 0. So I'm going to put -2, and I can just put like 0 concavity like that. So now how about between -2, who thinks they know where it changes from concave down to concave up? Or at least where I was trying to make it.
Zero.
At 0. That make sense? So this whole piece here is concave down. That whole thing right there, from -2 to 0. And again, you can see, like, look at the tangent lines. Do you see how the slopes are decreasing? Okay, so that's concave down, so it's a negative second derivative. And then where does it change from concave up back to concave down?
2.
At 2. This is where I was having trouble getting the function to look nice. It's challenging to make it go concave up to concave down and also have it be nice and differential there. But At least coming up with a piecewise function. Okay, so are we okay with that? Concave up. Look how happy he is, concave up. And then it switches to concave down, like that, that's concave down. So just looking at concavity, there was no concavity, then it was concave down, then it was concave up, and then it was concave down. Now that is all happening sort of independently of the function went decreasing, increasing, decreasing, increasing. Right? Yes.
Why doesn't the concave like down up start at 0?
It does. So,
0 to 2. Okay,
Yeah.
so start to finish. That's okay.
yeah, in this little section here, the derivatives are increasing.
Okay.
Concave up. And then, yeah, once you hit 2, it switches to now the derivatives are decreasing. So if that movement stuff made sense to you, you could think of this as being like, if this was a position function, so a particle that started in a positive position, went backwards, forwards, backwards, forwards. His velocity went left, right, but his acceleration went no acceleration, negative acceleration, positive acceleration, negative acceleration. Okay. All right. So we've answered a lot of these questions already. How about B? So B, are we okay with? On what intervals is F increasing? We should clarify the notation here, I guess. So I'm going to erase this. Is this, everyone okay with this? Fine, okay. All right, so where is our interval increasing? When is F? So F is increasing, now maybe in parentheses, that's whenever F prime is positive, right? So my interval would be from -2 to -1, union with the interval from 1 to infinity. Make sense? That U is just union, meaning it combines the two sets into one big set. How about where is F decreasing? Of course, decreasing means that the derivative is negative. So that would be from -infinity to -2 and from -1. Notice we're not using the square brackets because I wouldn't say that say at 1. At 1, it's not increasing or decreasing. It's changing from decreasing to increasing. We okay with that? Okay. C. At what x values does F have local extrema? Yeah, maybe we can figure out from the context, like extrema, sounds like extreme. So it's the extreme. Now, local extremes would be in your neighborhood. Are you the lowest or highest point? Versus a global extreme. What? What, you? Yeah. For joke telling, yes, of course. Yes, best joke telling. Best joke telling. But I mean, that makes sense just intuitively, right? You can be the fastest person in your neighborhood, but then you're not necessarily the fastest person in the world, right? So, like for example, here's a good point right here. Do you see how that point would be a local max? So let's list them out. So let's get the local mins. And it just says find the x values. So local mins happen, that's what Trey said, -2, right? -2, and then at +1. Make sense? Again, those are just the x values. So local min right here, local min right there. those two low points. How about a local max? Yes, a negative one. Cool beans? So there's the local max. This diagram's getting really cluttered. So there's the local max. Local mins are these two little valleys there, which also raises an interesting point. Does the derivative have to exist at a local min? Not necessarily, it could be pointy. Global extrema. Is there a global max? Right. So this is like, that's like saying, what's the biggest number? There isn't one. Okay. But there is a global min. So the global minimum would be -1, and that is a y. Typically, this is kind of context dependent. They might ask you for where does the global minimum occur, in which case you might name a point. But usually if it just says, what is the minimum of this function, they're asking for the minimum y value the function produces. What's up?
So why would it be -1?
Because that's the smallest y value that the function produces. If I draw my graph better, they both hit -1.
Oh,
Now I might make
I
it
see what you're saying.
if I'm taking a test, say you're in college and this is a question, I would write this, and I would maybe in parentheses write this occurs at the x values -2 and +1, just to clarify. Okay, on what intervals is the function concave up or down? So So anyway, hope this is all making sense. If you thought we were overanalyzing graphs in pre-calculus, this is taking it to a whole other level of really getting every possible property of the graph that we can describe. So concave up, remember concave up is when the second derivative is positive. Or you could think of that as when f prime is increasing. F prime is increasing. So when are we concave up?
0
From 0 to 2. Keep in mind that's an interval, not an ordered pair. It's not the point 0, 2. It's the interval of x values from 0 to 2. And then almost out of room here. Concave down. Now remember, concave down is when the second derivative is negative, aka when f prime is decreasing. So what do we get here from
-2 to 0 and then you do 2 to infinity?
That's infinity. Was it your guys' pre-calc class where someone one time was like, I was wondering all year what that stuff was?
Maybe.
I did.
Our class made fun of you for something.
That is an infinity sign. No, it wasn't. It wasn't her. It was someone. Someone was just like, yeah, it's that weird symbol. I'm like, yep, infinity.
Our class
Okay.
made fun of you for using the two circles instead of like the sign. I do two circles.
Okay, so point of inflection. What the heck is that? So, has anyone ever heard the word inflection point in like maybe an article or something that wasn't really about math? It might have been about something. It could be political or financial, economical. Anyone?
Probably.
Well, an inflection point is when the concavity changes. So, so like for example, at 0, That's an inflection point because it changes from concave down to concave up. And then same here at, and I should say at 0, 0. And then also at the point 2, 1, it changes from concave up to concave down. This is kind of a weird one. I mean, you could probably call this an inflection point. We're not going to worry about getting some sort of technical definition, but it's changing from 0 concavity to negative concavity. So you might call it that. But typically, they say, most definitions would say that the tangent line has to exist there. So it can't be like a pointy change. Here's where you might have heard it. Here's the context where it's relevant. Is say you're like, say you got a company, the company's kind of growing, right? That's good. That's what you want. Here's how much money you're making or revenue or something. Here's time. And so is this the kind of growth you want to see? I mean, you're growing, like you're increasing your revenue, but the rate at which the revenue is increasing is decreasing. So notice, like at first, like, whoa, we're increasing at a very high rate, high derivative. Okay, those derivatives are getting smaller and smaller. And then you're kind of fearing, well, what if we continue being concave down? That's bad. So you hit an inflection point. That's a lot of times it's used in a good context. Oh, we hit this inflection point into a concave up function, and now our rate of change is increasing. So that makes sense.
So is it like points when the graph changes, basically?
When the concavity changes.
Okay.
So back to this one. The point 0, 0 is an inflection point, and the point 2, 1. And that happens, you can see it on here, right? We change from concave down to concave up, and then we change from concave up to concave down at those two spots. Make sense? So just to clarify, these two in blue here, those are the inflection points. Inflection point is a point on the graph where it's changing from concave up to concave down, or from concave down to concave up, the reverse. Make sense? Okay. I want you guys to do them on your own, but I guess for the sake of this high production film here, maybe we should do one more together. Outstanding audio. Highest quality only. We'll do two together, and then you guys can do your own. Feel free to go ahead of me if you want, but for all the fans at home, all the millions of viewers. It's kind of weird how much video of myself now exists on the internet. It's kind of weird. I never intended to ever have videos of myself be on the internet, but now they're out there.
Now the government's spying on us.
Oh, the government, yeah. That's why I only use DuckDuckGo. Because Google, they want to send me advertisements for things like hats and skis.
You know that
No, Google, don't send me advertisements for skis.
TikTok, I feel that you're a teacher.
Oh, TikTok knows.
Have you seen the physics teacher on TikTok, Mr. Hall?
Which one is that?
I don't know his name, but he's like blew up on TikTok.
Sean sent me a TikTok recently where it was some physics guy, and he goes, I've been getting a lot of comments and messages of people complaining that, oh, physics is so hard, math is so hard, what can I do to, and he just ends it with being like, okay.
Yeah, that's it. He'll be like, he'll say stuff like this. He'll be like, just do it, just like do the homework.
The comments were pretty funny. They were just like, I showed you guys the organic chemistry TA one, right?
No.
I didn't show it to you? Okay.
I watched his YouTube videos all the time, but I didn't help.
The physics guy?
No, are you talking about the YouTube guy who does the tutorials?
No.
Okay.
I'll show it to you at the end of the class. We'll have time. I'll have to find it. So, okay, there's the graph. Let's get the number lines. Okay, where is my let's identify all what they call the critical values. Critical values would be any number, any x value, where the function is either has a zero derivative or an undefined derivative. Because those are the spots where it's going to change from positive to negative, or vice versa. So what's the first spot you see? How about this vertical asymptote, right? And then this Snapchat machine. Louisiana trying to call me. Probably legit, right? Should have answered. 0. And then how about 2? Everyone okay with that? Okay, so to the left of -2, pretty clearly positive slopes between -2 and 0. Oh, it's still positive. So that's something to watch out for, guys. What a common misconception among students is they draw this number line and just go plus minus plus minus plus minus. They alternate, but that's not always the case, right? And then we go negative slopes, and then switches to positive slopes. Okay. The other common misconception, guys, is people assume that any critical value means the derivative is 0. Which you can see it's a reasonable misconception, because a lot of times your function does something like this. And yeah, when it changes from increasing to decreasing, there is a 0 slope. But on this graph, is there any spot where the slope is 0? No, there is not. Am I listening, you guys, or does this make sense still? So let's get the F double prime number line. So again, this one is, where is it concave up or concave down? So, by the way, any spot with, oh, I missed one. Do you guys see the one I missed?
It's -1.
-1, yeah.
I was wondering.
Just testing you, obviously. Just testing. Not that I just missed it. That would never happen, right?
Yeah.
Impossible. Okay, so yeah, that's a point. That can be a little tricky, right? But that's a point that I got to consider, because can you guys see how the left half of this little doodad here is concave down and this is concave up? Is that can be challenging for people to kind of wrap their heads around the first time they see it. But so let's just write it in. So this is concave up. This is concave down. This part's concave up. How about this? Is that concave up or concave down? Concave up.
We have specific C.
Here's a good way to kind of, this is how other people, well, I probably shouldn't have said that, because I'm like, well, the water would just slip right off. I meant like parabolically, like, concave up parabola would hold water, concave down parabola. But it may be simpler as like, that's actually a good technical definition of concave up, is that if you draw a tangent line on it, what do you notice about that tangent line? Well, it could just as easily be like this. So these are both concave up. The tangent line is below the curve. Versus, this is concave down, and so is this. If I draw a tangent line, what do you notice?
Oh.
It's above. So the best definition of concave up is just to say that the second derivative is positive. But that's not the most intuitive, right? To say, oh, the second derivative is positive, it's hard to visualize that. But so anyway, as you can see, if I drew a tangent line here, I'd be above the curve, so it's concave down. And if I drew a tangent line here, it's below the curve, so I'd be concave up. Anyway, so between 0 and 2, it's concave down. And then between 2 and infinity, or from 2 to infinity, what's that, concave up or down?
Down.
Down.
Wait, when concave down, wouldn't that mean that it's negative? A
The-
prime is negative,
Mhm.
not if it's concave down.
Yep. Did I mess any up?
Well, you said 0 to 2 was concave down.
No. 0 to 2, this curve here is concave up. Okay, so this section here Look at the tangent lines. If you move from left to right on this curve, what kind of slope is that? Extremely negative, like negative 100, right? And as you move along, not so negative, not so negative, not so negative, you're getting to a point eventually where it's almost zero. So as you can see along this curve, the derivatives are actually increasing. And if your derivatives are increasing, then your second derivative is positive, which means you're concave. You guys will, if it's not making sense right away, it's okay. It often, for most people, it takes a couple, maybe hours of exposure and practice with this before it starts to click, but it'll click for you, I promise. You'll start to get it. So just remember this, these are a couple good examples. This is concave up, this is concave up, this is concave down, this is concave down. They're noodles, actually. Look at the noodly woodlies. You like them? If you think about it, this actually fully describes almost every possible type of, because this is concave up and increasing. This is concave down and decreasing. This is concave down and increasing. This is concave down and decreasing. That's all, that's every possibility, right?
Society.
We live in a society, exactly.
Would the tangent lines be considered inflection points?
Oh, or you mean the asymptotes?
Asymptotes.
No, this guy, you could maybe argue that this is an inflection point because it's changing from, it's a point on the graph
Isn't one also an inflection point?
at one.
Yeah. No, it's a negative one, sorry.
Oh, that for sure, yeah.
Why would you have to argue to this? Isn't it just
It depends on your definition you're working with. This is in a class where we're going to try to get into like, some calculus classes you might be really focus on definitions. So let's say your inflection point definition is a point on the curve where the tangent line exists and the function is changing concavity. Then with that definition, that this would work because there's no tangent line here. But I think for our purposes, it makes sense to call this an inflection point. So our inflection points would be at 2, 1, and -1, 0. Everyone okay with that?
-2 would not.
What?
-2 would not.
No, certainly not. So yeah, any vertical asymptote, we'd say that there's no point on the function there, so there can't be an inflection point. Let's get, we're kind of skipping ahead here, that's okay, but we're almost out of time, aren't we?
Yeah.
Okay. You guys can get the rest, right? I mean, does this have any, let's just go through verbally. Any local maxes? No. Any local mins? That point right there. This is an inflection point, but it's not a max or min.
It keeps going.
Because yeah, any global max or global min?
No.
No, it goes to infinity at negative infinity. Where is it increasing? Well, it's increasing wherever the derivative is positive. Where is it decreasing? It's decreasing wherever the derivative is negative. Same thing for concavity. It goes concave up, concave down, concave up, concave up, concave down. And then we already talked about the inflection point. So that's it for us.
Oh.